This lesson is kind of an introduction to waves. We're going to talk about the different types of waves and different properties of waves. It's going to be, some new terms, some terms that we've seen before. Alright, waves are important. Waves are important and interesting because they transfer energy without transferring matter. So usually, energy is transferred via matter. But waves take that energy and they pass it along from one matter to another, but the matter itself doesn't move. Most waves require a medium, some sort of matter to travel through. For example, if you scream in space, no one can hear you. If you clap your hands in space, no one can hear you. Okay? Electromagnetic waves are the only exception. They can travel through a vacuum, so they can travel where no matter exists. Now there are two types of waves. There are transverse waves and longitudinal waves. Transverse waves vibrate at right angles to the direction of the propagation. Alright, so they go up and down, up and down. An example of a transverse wave is light, and you'll see this constant quite a bit. The speed of light, the speed of electromagnetic waves, is 3 times 10 to the 8th. This is in a vacuum, and this is in air. Light also can be polarized, and we'll talk a little bit about that in later lessons, what polarization means. Longitudinal waves are waves that vibrate in the direction of propagation. An example of this is sound. So if you see this picture down here, what speakers do is they vibrate sound, okay, and has different waves, and your ear takes it in and interprets the sound. Now, at 20 degrees, sound moves at 343 meters per second. Now, temperature makes a difference, and medium makes a difference as far as the speed of waves go. Now, I said light is an example of electromagnetic waves. This is an image from Wikipedia. I really like this image. Basically, electromagnetic waves are a whole bunch of things. Radio waves are the same type of waves as the light you see. Same as microwaves. Infrared, visible, ultraviolet, X-ray, and gamma rays. The only difference is their frequency and wavelength. We see in this small visible range, but all these others exist. Now you are responsible for knowing which waves have more energy, which waves have, which frequency. Higher frequencies mean shorter wavelength. Here, I'll zoom out. Higher frequencies mean shorter wavelength. And you have to keep track of what goes where. You are responsible for this. So I come up with a couple of tricks. One, I always start with visible light. It's what we're most comfortable with. So you start with Roy G. Biv in the center. Now, on either side of Roy G. Biv is infrared and ultraviolet. On the side of red for Roy is infrared. On the side of V for violet is ultraviolet. Okay, so Roy is the lowest, so infrared is even lower. Okay, I also have it in terms of what's more dangerous after that, or what do we use less often. We use radio waves and microwaves, okay, a lot more often, and they're a lot less dangerous, so we go radio and then micro. Now when you get into higher frequencies, you start getting into things that are more dangerous, such as X-rays and gamma rays. Alright, X-rays are more dangerous. So higher frequency is higher potential damage. And I think about it that way. This last one, we have UV rays, sunburn, ouch. X-rays, radiation, little ouch. Gamma rays, woo, big ouch. So the ouches go up. Now, here's a nice, wonderful, awesome equation that is the Ohm's law equation of waves. V is your velocity, the speed of the wave. Sometimes it's the constant c if you're looking at electromagnetic waves in air and vacuum. Okay, sometimes you'll see c equals lambda f or f lambda. Okay, but basically c is just v in certain situations. F is your frequency, units of hertz. Hertz is the unit of 1/seconds. Lambda is your wavelength, and the units in meters. Wavelength is the length before the wave starts to repeat. And we'll go over wavelength a little bit more later on. You'll see some nice visuals. Frequency is the number of waves per second. And we've already seen frequency, and we've also already seen period. This is the period equation that's not in your reference table. Period is 1/frequency. And period is the number of seconds per wave. So frequency, number of waves per second, period, number of seconds per wave. So they're the inverse. Now, a quick note. We've talked about the speed of sound, v. Well, v can be 3 times 10 to the 8th if you're talking about electromagnetic waves in air or in the vacuum. V could also be 343 if you're talking about the speed of sound in air. But speed of sound changes depending on the temperature. So speed of sound in air changes. Where you have V naught of 341. Now, why is it 341? Or sorry, 331. The velocity of air at 0 degrees Celsius is 331. So we use that, think about it as the V naught. That's the V at 0 degrees Celsius. 0 is 331. And then we take the square root of the temperatures in Kelvin. So let's say it's 20 degrees Celsius. That's 293, right? So 293 divided by T naught, which is 273. And if we multiply that together, we get 343. So that's where 343 comes from the basis times that. And just a hint, remember, when you're solving from Kelvin to Celsius, you're adding 273.15. Now, wavelength. We have 2 types of waves, so we have 2 ways to look at wavelength. Wavelength is the shortest distance between points before the wave starts to repeat. Oftentimes it's easy to look at it as a crest to a crest or a trough to a trough. So high point to high point, low point to low point. Crest is the high point, trough is the low point. So this is a wavelength. This is a wavelength. Though you could also look at it at a middle ground. For example, from here to here is a wavelength. Here it's at the center going down. Here it's at the center going down. It's not here because here it's at the center, but it's going up, so it's not repeating yet. Sound waves, it's the distance between compressions. So distance between the same part of the wave. Compression to compression. Okay. Now amplitude. Amplitude is the distance of the maximum height or depth from the center. So amplitude is right here. Okay, so if you looked over here, let's say this said 3 meters, so then your amplitude would be 3. Well, this would have a smaller amplitude of, let's say, 1. Now, Crest, as I said already, is the part of the wave with the greatest height, while trough is the part of the wave with the greatest depth. Waves are energy. Waves transport energy, not medium. And the heavier the medium, the more energy needed to get the amplitude. So, if you have the same amplitude, and this one is traveling through air, and this one is traveling through water, and they have the same amplitude, this one has more energy because water is a heavier medium. You got to put a lot more energy to vibrate it. So think about the steps you take. You're walking through air versus you're walking through water. It takes a lot more energy to walk through that water. Same with the waves. Now, let's look at some relationships. Frequency doesn't change. So if you go from one medium to another, frequency does not change when you move between mediums. So for example, you have a wave, and it hits over here, it has air, over here it has water. If it has a frequency of 2 over here, it will have a frequency of 2 over here. Its velocity will change, v equals lambda f. Its velocity will change and its wavelength will change, but its frequency will not. So you'll still have a frequency of 2 lambda equals v. Now, if you went from air to water, your velocity would go down, which means your wavelength would have to go down as well. Now, velocity doesn't change if your medium doesn't change. So you can do whatever you want to the wave. You can change its frequency, you can change its wavelength, you can change its period, you can do whatever you want. But as long as you're in the same medium, your velocity will be the same. You can travel from air into water, into helium, and back into air. As long as that air is at the same temperature, your wave will be traveling at the same velocity. Now, wavelength, you'll see that basically will always be the thing that changes. Okay? You can drive it and say, okay, it will have this wavelength, and if you want to use that control, you can, but unless told specifically that your wavelength isn't changing, that's usually what will be changing. Okay, so an example. Identify the frequency of the wave. Well, down here we have time in milliseconds. So we have to find out how long it takes for one wave. So if the wave starts here, it goes up, it goes down, and it ends right here. So you get one wave in 4 milliseconds. Frequency is your number of waves per second. So you get one wave in 0.004 seconds. So your wavelength, your frequency is 250 hertz. If this is a sound wave traveling through 20 degrees Celsius air, what is the wavelength? Well, V equals lambda F. So 343 equals lambda 250. So our wavelength is 1.372 meters. If the sound wave is traveling into a different medium with a velocity of 298, what is its frequency? Frequency doesn't change when traveling into a different medium, so your frequency is still 250 hertz. But you do have a new wavelength. V equals lambda F. 298 equals lambda times 250. And your new wavelength is 1.192. Okay, that's it for the video. Good luck on your homework.